Hi, I'm Akshay, and I'll be talking about bounding the sum capacity of multiple access channels with and without assistance. This is joint work with Felix Leditzky, Vikesh, Siddhu, and Graeme. A multiple access channel, or MAC for short, is any channel that has multiple inputs and a single output. One can show that the sum capacity of a multiple access channel can be written as the maximum of mutual information between the senders and the receiver, subject to the constraint that the input probability distribution is a product distribution. And because of this constraint, the optimization problem involved is non-convex. And for this reason, people usually look for upper bounds on the sum capacity by performing a relaxation of the optimization problem. Specifically, Calvo and others propose dropping the product distribution constraint in order to obtain an upper bound. The first question that we would like to ask in this study is how would an upper bound the relaxation CAL on the actual sum capacity? And to answer this question, we consider a family of multiple access channels constructed from non-local games. By a non-local game, we mean a set of questions for each player, a set of answers for each player, along with a winning condition that determines whether a given pair of questions and answers wins the game. Given a non-local game G, one can construct the channel NG as follows. Alice and Bob send a pair of questions and answers into the MAC NG, and if they win the game, the channel transmits their questions noise-free. But if they lose the game, a randomly chosen question pair is transmitted by the channel. Leditzky and others argue that the sum capacity of the MAC NG can increase with the winning probability of the game. And for this reason, we allow for the possibility that Alice and Bob share a non-local correlation P and do local post-processing in order to generate their final answers, which along with the questions is input into the MAC NG. This procedure defines a new MAC, which is NG along with assistance from the non-local correlation P. Then, given a set of correlations C, we can define the C-assisted sum rate of the MAC NG as the maximum over all correlations P allowed by the set C of the sum capacity of the MAC NG with assistance from the correlation P. And we find that allowing classical correlations is equivalent to computing the sum capacity, whereas allowing quantum or no signaling correlations can increase the sum rate. On the other hand, we find that CAL sits at the top of this hierarchy. One of the main results of our study is an upper bound on the C-assisted sum rate of the MAC NG. This upper bound depends only on the total number of question pairs of the game and the maximum winning probability of the game when the questions are drawn uniformly and the answers are obtained using strategies allowed by the correlation C. This upper bound can be useful in obtaining separations. For example, for the MAC obtained from the magic square game, we can obtain a separation between the sum capacity of this MAC and the quantum assisted sum rate. In fact, our upper bound on the sum capacity is tighter than what was previously reported. In the same spirit, we look for separation between the sum capacity and CAL. And for this purpose, we construct a game which we call the signaling game, wherein Alice and Bob win if Alice can correctly guess the question that was given to Bob, and vice versa. We find that as the number of question pairs becomes very large, the sum capacity of the MAC induced by the signaling game goes to 0, whereas CAL diverges. This shows that CAL can be a very bad upper bound on the sum capacity. Moreover, we find that the no signaling assisted sum rate is always less than CAL for this particular MAC. And this highlights the importance of the second question that we considered in the study, which is whether we can find better upper bounds in the sum capacity compared to CAL. To that end, we consider a family of two-sender multiple access channels, and we present an algorithm that can either compute or upper bound the sum capacity of any MAC in this family. If we provide a fixed precision to this algorithm, then the algorithm is guaranteed to converge to the sum capacity within that precision. On the other hand, if we provide a finite number of iterations to this algorithm, then the algorithm outputs an upper bound on the sum capacity. To check the performance of our algorithm, we give an example of a binary MAC with the property that the sum capacity of the MAC is less than CAL. We find that our algorithm computes the sum capacity to a small enough precision, showing that one can do better than CAL. Thank you.